Today we discuss section 3.3 about Hopital rules. This is a very powerful technique to find the limit of a function. Recall that we have very convenient tools from chapter 4 to find the limit of function, namely the compatibility of the limit concept with algebraic property. So in many cases, you will need to find the limit of each term in an expression and then compute the value combining these um, terms. However, in certain cases, the step of combining these terms together has some difficulty. That is, for example, you cannot divide by 0. So if you have a quotient and the denominator is approaching 0, then you don't know what to do with that. The correlation of these difficult cases is called indeterminate forms, and the aim of today's discussion is to develop a technique called Hopital rule to find limits of these indeterminate forms. So the indeterminate forms might be the case 0 divided by 0, or infinity divided by infinity, or infinity minus infinity, or 0 times infinity, or 1 to the infinity, 0 to the 0, or infinity to the 0. These are the most common indeterminate forms that you're going to see in this class. So we start with a very simple case. Let fg be defined on an interval from a to b, and fa equal to ga equal to 0, and gx is different from 0 for all x between a and b. If f and g are differentiable at a, and if g prime of a is different from 0, then we have the limit when x approaching a plus fx divided by gx equal to the derivative of f evaluated at a divided by the derivative of g evaluated at a. So in other words, the limit of the quotient of these two functions is equal to the quotient of its derivative. And here we have x approaching a plus means x approaching a from the right, as you can see in this picture. So the proof of this theorem gives the prototype for other proofs that you're gonna see in this class, in this section. It's just simple. So we have fx divided by gx equal to fx minus f of a divided by gx minus g of a. The equality holds because fa and ga are equal to 0. So here we can rewrite this quotient as fx minus f of a divided by x minus a as the numerator, and gx minus ga divided by x minus a as the denominator. That is, we divide both the numerator and denominator by the expression x minus a. This is motivated by the observation that now both the numerators and denominators are expressions related to the derivative constant. So in particular, here the numerator here is approaching f prime of a when x approaching a, and the denominator here approaching g prime a when x approaching a. So this is how you can relate the quotient of these two functions with the quotient of their derivative. Rigorously, we proceed by taking limits of both sides of that equation. So the limit of the quotient fx divided by gx equal to the limit of this expression fx minus fa divided by x minus a in the numerator and gx minus ga divided by x minus a in the denominator. Now the limit of the numerator is f prime of a. The limit of the denominator is g prime of a. Then we have the conclusion of this theorem. So this theorem and its proof basically tells us how to relate the quotient of two functions with the quotient of their derivatives. Of course, here we restrict ourselves to special condition, namely fa equal to ga equal to 0. For a general case, we had to modify this argument in an appropriate way, but the idea stays the same. Next, we're going to state what we call the Cauchy mean value theorem. In order to explain this theorem, first recall the original mean value theorem, which say that the quotient fb minus fa divided by b minus a is equal to f prime of c for some c within the interval from a to b. Of course, there's some condition to make it work, but this is the main equation associated with the mean value theorem. Now, the Cauchy mean value theorem basically generalizes that statement for two functions. Let f and g be continuous on the interval from a to b and differentiable on the open interval from a to b, and g prime of x is different from 0 for all x in the open interval from a to b. Then there exists c in the interval from a to b such that the quotient fb minus fa divided by gb minus ga is equal to f prime of c divided by g prime of c. In other words, the mean value theorem is a special case when the function g of x here is just equal to x itself. And the Cauchy mean value theorem is again a generalization of that mean value theorem. The proof here basically in the same spirit as what we saw earlier, using Rolle's theorem and the construction of Van Nuys function. Now we can establish the first version of Hopital rule. Let R tilde be the union of the set of all real numbers with these two special symbols, plus and minus infinity. Let f and g be differentiable on the open interval from A to B for AB inside this extended set, such that g prime of x is different from 0 for all x inside the interval. Now suppose that the limit when x approaching a plus f of x equals 0, and the limit when x approaching a plus g of x is also equal to 0. Then if the limit of the quotient f prime x, g prime x, when x approaching a plus is equal to some number L inside this extended set, then the limit of the quotient of these two original functions is also equal to F. So this is the Hopital rule for indeterminate form. Zero divided by 0. In this case, both the function f and h, f and g are approaching 0 when x approaching a. Then the limit of their quotient is equal to the limit of the quotient of their derivatives. So the proof of this theorem is based on that Cauchy mean-value theorem. Also, note that this is a statement for a right-hand limit. A similar statement regarding left-hand limit is proved in the same manner. The result for two-sided limits follows from the right-hand and left-hand results. Now, I would like to give you several examples to illustrate how the Hopital rule works. For example, here we consider the quotient sine x divided by x, and we would like to compute the limit when x approaching 0. So first, we observe that this is an indeterminate form because the limit when x approaching 0 of psi of x is equal to psi of 0, which equal to 0, which is also equal to the limit when x approaching 0 of the function x. That's why we can apply the Hopital rule part 1 to obtain the limit of this quotient by x divided by x is equal to the limit of the quotient of that derivative, and the derivative of the psi function is just the cosine function. The derivative of the x function is just equal to 1. So this is equal to the limit when x approaching 0 of cosine x. And this equal to cosine 0, which equal to 1. So the answer for this case is the limit here is equal to 1. So you see the Hopital rules here are very, very powerful techniques. If we just use the theorem about compatibility of the limit notion with algebraic properties, then you struggle with dividing by 0 here. However, the Hopital rule allows you to bypass that difficulty via looking at the quotient of that root. Now, the second version of the rule is the following. Let's consider the extended set including the set of all real numbers and the special symbols plus and minus infinity. Let f and g be differentiable on the interval from A to B, with AB belongs to this set of this extended set, such that G prime H is different from 0 for all H inside the interval. Suppose further that the limit when H approaching A plus of G of H equal to plus or minus infinity, then if the limit of the quotient of that derivative equal to L inside the extended set, then the limit of the original quotient is also equal to L. This is essentially the Hopital rule for indeterminate form. Infinity divided by infinity. Here is an example of its application. We consider the limit when x approaching infinity of e to the minus x times x squared. This can be rewritten as the limit when x approaching infinity of x squared divided by e to the x. Now we observe that the numerator here approaching infinity when x approaching infinity, and the denominator also approaching infinity. So that's why this is an indeterminate form, infinity divided by infinity. Apply Hopital rule, part 2, we have the limit of x squared e to the x going to be equal to the limit of that derivative, which is 2x divided by e to the x. But this still indeterminate because here the numerator here still approaching infinity, the denominator still approaching infinity. So we had to apply the Hopital rule again. And look at the quotient of that derivative. So derivative of 2x equals 2. The derivative of 2 to the e to the x is still e to the x. So now we have 2 divided by e to the x, which approaching 2 divided by infinity, which is equal to 0. So in general, the rule of thumb is that the logarithm function is approaching infinity slower than the power function, and the power function is approaching infinity slower than the exponential function. So we have looked at the rules part 1 and part 2 dealing with two special indeterminate forms, 0 divided by 0 and infinity divided by infinity. How about other indeterminate forms? Well, the general framework is that other indeterminate forms can be reduced to the previously considered cases by algebraic manipulation. That is, we can use the logarithm function and the exponential function to manipulate some expression to reduce it to one of the two previously considered cases. Here is an example. We consider the limit when x approaching 0 plus of the difference 1 over x minus 1 over psi of x. We observe that when x approaching 0 from the right, namely x bigger than 0, then 1 over x approaching plus infinity, 1 over psi of x is also approaching plus infinity. So here we have the case infinity minus infinity, which is an indeterminate form. So how do we do it? Well, first we just rewrite this difference as psi x minus x divided by x times psi x. And then we observe the numerator here approaching 0 when x approaching 0. The denominator also approaching 0. So this is 0 divided by 0 indeterminate form. So in this case, we just did a very simple algebraic manipulation to transform the infinity minus infinity indeterminate form to the 0 divided by 0 indeterminate form. Then we can apply the Hopital rule part 1 to obtain the limit here equal to the limit of the portion of that derivative. Now, the derivative of psi minus x is just equal to cos x minus 1. The derivative of x psi x equal to psi x plus x cos x. We observe that still the numerator here approaching 1 minus 1 equals 0. The denominator approaching 0 plus 0 equal to 0. So it's still in indeterminate form. So we have to apply the Hopital rule again. And when we apply the Hopital rule again, the numerator becomes minus psi x. The denominator becomes cos x plus cos x minus x psi x. The numerator here approaching 0. The denominator, luckily, approaching 1 plus 1 minus 0, which equals 2. So this expression no longer indeterminate form. And we can't apply the Hopital rule anymore. Instead, just apply the compatibility result to deduce that the limit equal to minus 0 divided by 1 plus 1 minus 0, which is 0 divided by 2, which is equal to 0. So this example, the algebraic manipulation is quite simple. Now, the next example, the algebraic manipulation is a little bit more involved. Here we consider the function x to the x when x approaching 0 plus. We had to be creative with algebraic manipulation in a sense. So let f of x be the function x to the x. And this is indeterminate form 0 to the 0. We consider the function g of x, which is the logarithm of the function f of x. And the advantage of taking the logarithm is that it's gonna remove the variable x in the power part of the expression. So g of x is just equal to x times ln of x. And g of x is indeterminate form of type 0 times minus infinity. We can rewrite it as the portion of ln x divided by 1 over x, which is in infinity divided by infinity indeterminate form. Applying the Hopital rule, now then we can deduce that the limit of the function g of x equal to 0. That's why the limit of the original function f of x must be equal to e to the 0, which is equal to 1.